Oh, hi everyone. Good afternoon. Thanks for joining the talk, and I'm very honored to be the last one to present. Thank you for the introduction. Also, the title of our work is Import Library, Import Liability: Analyzing Information Collection of Third-Party SDKs. So this is the work done by the collaboration between university and industry. I'm Kailong from NUS, and I'll present more information on our group shortly. Before the next step, here is a roadmap of our today's talk. And first, I'll introduce our team member. Then I'll quickly go through the background related to this work, and then I'll talk about SDK-related issues that we focus on, and then the technical details followed by that. And lastly, I'll conclude the talk. So about us, so our team has 4 members, and unfortunately, due to the travel arrangements restrictions, only I can make it here since I always in Singapore. And we're working on the mobile security and privacy related research. And Dr. Bai is a senior lecturer in the University of Queensland. And I am a postdoctoral researcher in NUS. And Mr. Zhang Qing and Zeyu are from ByteDance Research Lab. So the rest of the team member will be joining this session online, and they're happy to answer any questions if you at the end of this session. Okay. So let's next I'll share some background information. So personal data protection has been increasingly emphasized when developing applications. So recent years has seen many privacy regulations enforced around the world, such as Pdpa here in Singapore, CCPA in California, and Gdpr in Europe. For example, Gdpr Article 5 has defined 6 data processing principles to guard the security and privacy when handling user private information, as shown here. So they include lawfulness. Oh, sorry, can you see the pointer? Okay, the first point is lawfulness. Second is purpose limitation. Third is data minimization. The fourth is accuracy. Fifth is storage limitation and security. So in particular, the first principles are related to our work. More specifically, the lawfulness, which requires the personal information to be processed lawfully, fairly, and transparently. And for the purpose limitation, which requires the information to be collected for specific, explicit, and legitimate purposes. And specifically, the data processing information should be made clear and precise to the users. So since the enforcement of GDPR, huge amount of penalties has been applied to companies which fail to observe their regulation requirements, running into like hundreds of millions of euros just for one data controller. Well, here this data controller is actually the service provider, which is also known the company. So the accumulative fines for GDPR in the first photo here has been skyrocketing from 400 euros back in 2018 when the GDPR was just introduced, and to a staggering of over 1.3 billion euros at the end of 2021. So from the table here on the right, for example, we list top 8 target amounts of fines to the data controllers so far. And the most involve the violation of GDPR Article 5 and its related data processing principles. And note that the fine from a certain data controller in 2021 July, there alone is over 700 million euros, which makes Luxembourg the top country in terms of GDPR fines so far. Given the emphasis of privacy on legislation side, the service vendors are taking actions to engage in the compliance to avoid this kind of privacy-related fines. So one of the noticeable changes are the privacy dashboard added to the operating systems. So despite their capabilities to show the permissions and accesses granted to the applications, the detailed data collection behavior from these applications are still unknown. For example, the photo album access will only let us know that one app was granted this kind of permission, but its activity for accessing the photos or which exact photos are being accessed or uploaded are still not known to the users. And the detailed privacy issues are unable to be solved by just simply adding this kind of privacy dashboards. But from them, we have already identified the finer grain problem of private data management. So, and nowadays for application development cycles, third-party SDKs, also known as third-party libraries, are widely used, especially in Android applications, so that the developers have the ease for their development and with enhanced functionalities. However, the incorporated libraries will also bring new privacy issues to the host applications and blur the accounting between the application code and the library code. So for example here, around 80% of the application development, the developers do not update their third-party SDKs after embedding them in applications initially. So this will probably become the backdoor for adversaries to abuse the user's private data. So now now this takes us to the topic of our work, the privacy data management issues among the third-party SDKs. So we have identified the problems in three aspects, namely for the developers, for the service vendors, and for the audition process. So for the developers, the problem is rooted in the lack of security and legal expertise in them. So first, it is difficult for them to determine the data collection behaviors from those SDKs. And second, the proper use of the SDKs, the improper use of the SDKs will leak or reveal more private information to the third parties. And third, the private information could be abused if the developers are using the SDKs that are not approved or audited by the legal department or team of the company. So the not approved SDKs are typically those from the latest updates or from the non-audited versions. So for the service vendors, the origins for these data sharing management problems are rooted in the poor management of the developed SDKs. So first, there are typically various versions of SDKs due to the continued development or the maintenance of their provided services. However, the vendors typically maintain documents only for one version of the SDKs. At the same time, the update for such kind of documentation is not done in a timely manner. So, and also for second, the released documentation on the vendor's official site is usually not for the multiple products. So this will result in some less specific information given on a specific SDK. And third, within the official documentation, the information on the data collection usage is sometimes lack of details, or it's vague or imprecise. And regarding the audition process for the third-party SDKs, it is hard to adopt a uniform approach to examine the data usage and data collection behavior because the method for collecting data are diverse. For example, the typical way to get the app list installed on a device is to use the methods such as the get installed applications or get installed packages. But an unconventional way here is to read the directory of the SD card Android data. The reason is so after installation or the usage of an app on the device, there will be a folder named after the application package under this directory. And then the user, the adversary could access the similar data, but in a completely different way. However, this approach is not working anymore after the Android 11 due to the system patch on this potential private information leakage. And the usage of the reflection invokes or hidden APIs also makes it less straightforward for the audition at times, because there are flexible ways for passing the parameters. For example, on the figure to the right, the get device ID returns to the IMI. However, it could also be passed as a parameter instead of a string here from other locations. And this makes it hard to audit such kind of APIs. And moreover, the use of black technologies would definitely increase the difficulty for audition. For example, the read files will enable obtaining some kind of private information. An example is like, it is possible to directly read the ARP file to obtain the BSS ID. And also, the N-day and 0-day exploits also help retrieving private information while retaining hidden from the audition. The example here shows that it uses an 0-day exploits that reads the telephony SIM info list from the database. And by doing it, the adversary can get the ICC ID, which is a unique ID for the SIM card, and IMSI, which is a unique mobile subscriber ID. And additionally, there are several more other challenges regarding the SDK audition. One is because some techniques are heavily reliant on the network traffic, because they scan for the sensitive information that is uploaded to the inside the network traffic. However, this kind of technique could be easily defeated by just simply adding the encryption. And also, there are diverse data collection behavior and rules that makes the SDK audition kind of like complicated. For example, sometimes the application only periodically uploads the captured user information. And this will make it hard to track the data flow. And consequently, it increases the chance that we miss the data upload behaviors during the audition. And for some applications, the data collection rules are dynamically delivered. And therefore, only during the runtime we could know about the exact rules for the data collection. For example, the API invokes and data uploads. So now then, given all the private data management issues, it makes us wonder, what exactly does the third-party SDKs brings to us? Do they bring extra capability, or they just bring fines or liabilities or even Trojans? So we of course hope that we could they could bring us extra capabilities, and to better utilize their capabilities while mitigating the aforementioned risks, there have been techniques for bridging the gaps during the SDK auditions. So before presenting our techniques, I would like to briefly discuss on the pros and cons of the existing techniques for the third-party SDK auditions. So there are typically 5 I list here, and for the reverse engineering, it is highly precise in the reported issues. But here, highly precise means it is highly accurate, but not 100% compared to here which is conclusive. So conclusive means like 100% confidence and accuracy. So for reverse engineering, it is highly precise in the reported issues, but it typically requires a lot of workload for analyzing each SDK. So it makes it less possible or feasible to be deployed as a large-scale analysis technique. And in addition, the logics for some data collection functions could be missed or unreachable in the analyzed code segments. And for the network audit, it is right, just as I said, it's conclusive with detected issues. However, it is easily defeated, as I mentioned in the previous slide, that by simple encryption on the network traffic. And also, typically, it also would require the privacy analysts to dynamically test the app by sequentially visiting or interacting with the UIs on the app. So this will likely render less coverage due to the test coverage, and especially when the app is complex. And for auditing using official documents, it is easy. It's simple and easy to do. However, it is very unreliable because because that sometimes the data is imprecise, sometimes it's not updated, etc., etc. And for the hybrid techniques like taint analysis, combined with reverse engineering, it is highly effective while with mild drawbacks such as they still requires the manual efforts for confirming some output reports. And there is still unreachability issue that is rooted in the reverse engineering part. However, we find it is still suitable for large-scale detection because of its efficiency. So therefore, our approach is actually based on this type of technique. And lastly, for some organizations, they rely on the API invoke to audit the data collection behavior. And we find it very unreliable because the privacy preserving computing is widely deployed, and what they do is they perform the data manipulation and operations locally without uploading them. So in this sense, we should only consider those kind of data access just as access, but not data collection per se. So now let me share more details on the information on the technical parts. So for the taint analysis, it is a technique that we normally use to track and analyze the flow of a taint information throughout a program. And this technique has been widely used in the vulnerability mining. But for the privacy scanning, in this privacy scanning context, we would focus more on whether the privacy data is transmitted back to the server through the network channel. So we need to redefine the source and sink used in the typical taint analysis. So in this work, we define the source and sink as shown here, that the source is the privacy data from an API, and the sink is a data sending information methods of the app client's network library. So including the incoming URL headers body of a request. And for example, here, the get device ID is a source because it contains the target information which is a device ID here. And the sink is the set request property method, which sets the general request property of a URL connection. All right. And further, for our taint analysis, in this work, we based on our two tools. One is called Mariana Trench. It is an open source engine released from Facebook. And this tool defines the propagation rules by model and enables fast scanning compared to the other state-of-the-art tools that is currently available. And the other one is called AppShark, which has been developed by the ByteDance and has been originally used for the company's security vulnerability scanning inside within the company. So this tool actually defines the propagation rules by source and sink tuple, as we explained in the previous slide, and it is able to scan all the privacy-related API calls. And so we use both tool for the scanning task in this work so that we can have a more comprehensive mining of the data collection issues. And then we find that they actually complement each other quite well. So there are actually some issues from the original version of the Mariana Trench before we can directly apply to our task. We made some improvements to make the tool works better for our purpose. So one major shortcoming is that the original Mariana Trench is unable to take the static variable as source. This is because some private data are not directly from an API. For example, the Android ID and serial number. So in such kind of cases, the source cannot be defined directly with the type of the method. And to solve this problem, we have a secondary development of this engine that enables the support of defining the static variables as source. So this improvement greatly enhances its capability in tracking the private information flow. This because many private data are static variables. And another shortcoming is that the Mariana Trench does not handle the asynchronous calls very well. So in the previous verification results, we find that some taint propagation has been interrupted because of such kind of asynchronous calls. So then we make some modifications by adding a configuration file to describe such kind of tainted delivery from this such kind of cases. So as shown in the figure here, in the configuration file, we define the base class name, the method name of the asynchronous calls, and the callees. And for each callee, we include its method name, the return type, and our argument types. Okay, and now I would like to share the experimental results from our study. So we use these two engines to scan 211 SDKs from Google Play and some other platforms that I will detail later. And we manually verified the scanned results for the 37 SDKs. And according to the recorded results from our tool and this manual confirmation, we have shown to achieve an accuracy of 92%, with a recall of 88% and F-score of 0.9. And from them, we find that 41 SDK, from our results, from the reported results, we find that 41 SDKs out of the 211 actually upload the user's private data, which is roughly around 19 to 20% of the SDKs we have studied, as shown in this pie chart here. And the detailed types of private data being collected by the SDKs are listed in this histogram, and explicitly we focus on the listed 25 types of the private data. We note that among the 25 types, not all the types of data are collected, and we observe there is definitely some typical patterns for the targeted data types. For example, the most frequently collected private data include IMEI, Android ID, which account for 15 of the SDKs that collects them, followed by the IP, which with 12 SDKs collecting them. And the next, there are 11 SDKs collect Wi-Fi MAC addresses, BSS ID, and GPS. And 9 SDKs collect serial number and SSID here. So since the results of the taint analysis are not 100% accurate, so we further calibrate this reported results with manual reverse engineer and analyze their source code. So this is notably that is the only part in our approach that introduces the reverse engineering. And in this way, we minimize the required manual tasks or manual efforts in this kind of task. So to do the calibration, we first ensure that all the results of the privacy API calls are accurate, and then we scan the privacy API calls that appear in an SDK. And then we only need to review the results of the privacy API calls with no taint propagation. This is because the precondition for having a taint propagation is that the privacy API calls access the data. So in other words, if no data has been accessed, there is no taint propagation. For example, in this figure, our tool confirm in this scenario, like in this example, our tool confirm 4 API calls with data upload behavior. And here we number the sensitive API calls by a unique number, and different numbers represent different API calls. And we identified 5 API calls in total. And therefore, we only need to manually check the one API call that the 365, which is marked as unconfirmed. So, as a further illustration, we show some results of the SDKs we discover with these privacy issues. So, like I will show like 3 detailed examples for this particular SDK, but this for the identity of the SDK we blur out because the company's policy. But if you want to know more details, you can contact our team members later offline. For this SDK, it collects the cell location, which can be seen from the analyst reports here from our tool that the source is the cell location returned by this get cell location method, and we trace this information sync to this output stream here. However, we do not find any information on such data collection in this official privacy policy here. As you can read here, they do mention a few detailed IDs such as advertised ID and some self-created ID, but just no cell location. And similarly, another example shows here is that this SDK collects the GPS SSID and BSSID data from the user side, user device. So on the left figure here, we show that the similar reports on the GPS data, and for the SSID and BSSID data is conducted in a similar way, and the source is returned by the get altitude method, and the sync is similar, is the output stream. And once again, we do not find any data collection behavior declared in this SDK's privacy policy. And furthermore, there are even worse cases where the SDK collects personal data, but without even showing any privacy policies from its vendor. So in this case, our tool reports this GPS data collection from this get longitude a method, and then the sync is the byte array output stream. So, but we don't find any privacy policy associated with this SDK. So then I would make a summary of our work. First, I would like to summarize on the status quo of the data collection practices of third-party SDKs and their problems. So the majority of the third-party SDK vendors do not properly manage and precisely disclose their private information they collect on their own official sites. For example, many official descriptions of Android and iOS SDKs only contain private information collected by a certain version, which probably be outdated version or the one that without proper updates. And many vendors, another problem is that many vendors do not provide a dedicated policy for the private data collection for a particular SDK, and only rough descriptions. And worse more, in such descriptions, the terms used are sometimes ambiguous and not accurate. One example, some example is like some description would mention collecting data such as the Y-line information, but without exact detailing on what kind of data on the Y-line they collect, such as do they collect SSID, BSSID, IP address, etc., or all, and similar issues with other device-specific IDs. And the audition on the SDKs are challenging because of the heterogeneous techniques used for the data collection. And last is that some ill-purposed SDKs can be abused by the adversaries to target on the private informations from the users. And in summary, for our contributions and open source, for the contribution side, we have identified 40+ SDKs with inconsistent data information collection behaviors. And we have informed the relevant vendors and received their acknowledgement from them before this talk. And we have constructed a dataset on the private information collection for 200+ SDKs. And we hope to enlarge this dataset and keep maintaining this dataset with their updates and different versions. And we further seek to utilize our developed tools to scan and detect more related issues on the private data collection. And for the open source of the tools that I mentioned, so we plan to open source our improvement done for the Mariana Trench tool on our GitHub next month, and please keep tuned. And also, for lastly, I would show some details about the data that we got in our data set. So to derive the SDKs, we rely on this newly implemented Google Play SDK index, and we have collected all the 125 SDKs from them. And the rest are collected from platforms that from China. And then we plan to continue maintain this data set with added new SDKs. And yeah, that is my presentation. So thank you for your attention and time. And yeah, so thank you. Right. So if you have any questions, you can ask, and then if I cannot answer, my teammates will be on Zoom too. Yeah.
Yeah. There's a few questions there. Would having a SBOM, software bill of materials, help to analyze third-party SDK better?
Sorry, can you?
Would having a SBOM, software bill of materials, help to analyze third-party SDKs better? It's on the screen if you want.
Okay. The SBOM software bill materials help to analyze. Okay. Yes. Any comments from the collaborator part? I currently cannot. I don't know the definite answer for that. Yeah. So.
Yeah, probably let me try to take this one. I think the bill of materials basically means the analysts can be given more information about the SDK, right? So probably some of the SDKs are not open sourced in our research, and definitely there will be some limitation in such case because we need the source sync and also the data flow, basically to identify the data leakage. So yeah, agree. If we are given more information, the number one, we can find more leakage, and number two, the analysis can be more accurate. So, but to some extent, I think it's not quite easy to answer at this stage. It really depends on what kind of information we can be given. So I hope I partly answered the question.
All right, thanks, Dr. Bai. The second question
is, let me see.
Do you think Pdpa is comparable to Gdpr?
It definitely has many similarities, but maybe the terms are described differently. Yes, so I think our work is just focusing more on the GDPR side, but I think this work can be easily transferable to other kind of privacy regulations, such as like mentioned Pdpa. I'm sure Pdpa will have similar data purpose limitation and legitimacy on the data collection practices defined in the terms. Yeah.
Thanks. And the final one. Sorry, was someone going to say something?
Oh, I think
no. Yeah.
All right. What would you do if you manage to decipher obfuscated code that collects user data and does not declare privacy policy to user?
Collects user data. Oh, without. Sorry, can you go back to the question?
Can you put it on the small screen?
Yeah, right.
Yeah.
Oh, yeah, right. So okay. If you manage to decipher across your data that doesn't declare privacy policy. I think it's a very interesting question. So when you decipher, but I think in whichever way it has to. So as a developer, they have to declare. To transparently declare their actions to in their privacy policy, no matter whether this code is obfuscated or not. Yeah, I think this is my short answer. I don't know whether I solve your concerns.
I guess that would be the ethical way to do it, but there's a lot of scammy, dodgy.
Right. This is one of the challenges I think with obfuscation. But I think, so maybe I think we should also maybe have a further look into this issue later in the future work. Yeah.
All right, great. Are there any more questions from the crowd? Nope. All right, let's give all three presenters a round of applause again.
Thank you, guys.